I will try to show in this last lecture how to apply the method I introduced in the first two lectures to the study of Anosov flows. And in the first part, I will explain a bit how to set up a Freedom problem for an Anosov vector field using these anisotropic spaces. And then I'll explain some application to not exactly this part, but the concept of wavefront set and what I said about wavefront set of distribution to the study of the Mach length spectrum rigidity in the case of an Anosov surface. So it's some recent work that we've been doing with Thibault Lefebvre and Gabriel Paternoin. And I explain this because I find the proof quite nice, and it's and you can see that the wavefront set concept is important to this proof. Okay, so as I explained yesterday, we want to construct. The goal now is to construct an operator, which it will be the quantization of a certain symbol, such that H equal A of L2 will be a Hilbert space A will be invertible what else? It will map infinity to infinity. It will map distribution to distribution. And then we will like such that if I consider so X is the Anosov vector field, so X is an Anosov vector field, smooth. V will be a potential. So in the proof, I will not include this V, but everything works the same. It's a smooth potential. Is going to be Freedom on H. So here, as I said yesterday, one has to be a bit careful because when we talk about Freedom, one has to care about the fact that this is an unbounded operator. So we need to take it will be a map actually from the domain to H, from its domain to H, and the domain is going to be a subset of H. So as a map from a subspace of H to H. So in particular, we'll have a finite dimensional kernel and finite dimensional co-kernel. And for this, we will construct an operator Q, which is bounded on H, so that minus X plus V time Q is equal to the identity plus a remainder term, which I will call S, where S is going also to be bounded on H, and S is what we call quasi-compact. So S will be S0 plus S1, where S1 is compact on H, and S0 has a small norm, so let's say less than 1/2. And this is sufficient to say that in that case, 1 plus S is going to be a Fredholm operator. So here it's on the norm on H. It's going to be Fredholm on H. And then if it's Fredholm, it means we can invert it up to a finite dimensional operator. And this will give, if we take the inverse up to the finite dimensional kernel, we multiply by the inverse on the left, on the right, we'll get an approximate inverse with which will invert identity plus a finite dimensional projection. That's the idea. So, okay, so how to construct this A and this Q? Well, first, I want to start with the approximate inverse. So in my proof, I will, for simplicity, I will take V of x to be minus lambda, where lambda is a complex number. And in that case, minus lambda time identity, I mean. In that case, minus x minus lambda inverse is what we call the resolvent of x. F minus x. And this guy is actually explicit when lambda, if lambda has a real part which is large, there's an explicit inverse just on L2, for instance. So minus x lambda inverse exists on L2 and is given by minus x lambda inverse equal, so let me get it right, because there is a sign. It's minus t x plus lambda t. And this is nothing more than the flow. So here what I mean is that this is just f compose with phi minus t. Okay, and this, if you remember, this was the transfer operator. So I just pull back to invert this operator. I just pull back by the flow. I put this guy. And if the real part of lambda is large, this is actually converging. This is really easy to see. And this converges because exponential minus tx as an operator from L2 to L2 is just bounded by some exponential C0t. Okay, lambda is just a number, so if you want, maybe I write it like this. Sorry. It's just commuting with x, so. Yes, yes. Multiply the flow by just a small number, basically. So you know that if lambda is large enough, this actually converges from, and it's bounded from L2 to L2, and you can estimate. So in fact, to be convergent, you just need the real of lambda bigger than C0 here. So C0 is just the norm of, it's related to how the flow, it's like the Jacobian somehow that appear if you choose a measure to define your L2 space. Here you need, of course, you need a measure. So you fix a Lebesgue measure. For instance, with a Riemannian metric, this induce a C0. If it's volume preserving, C0 would be 1. Then you would get, you would just need to take real of lambda positive. So we know what is the inverse. And if you put the potential, it's more or less the same. You just need to include the term with the integral of the potential along the flow. So now we know what is the inverse of this operator in a half space. So we know that we have 0 here. This is C0. We know that in this region, minus x minus lambda actually exists on L2 as a bounded operator on L2. Okay. So it means that here I know what should be my operator Q when V is lambda, at least when V is lambda with lambda real part large. I have a very good guess of what it should be. The problem is the integral is infinite, so it's a bit tricky to deal with it on H. Because now I want to prove this thing for any lambda somehow. So what I will do, I will approximate my inverse. So I will choose now Q to be minus the integral from 0 to t, where t is a large number. And for just technical reason, I will also introduce a cutoff function, which I will put chi of t, where chi is the function which is 1 on a large interval up to t minus 1, and which is 0 after t. Okay, so in fact I could even put infinity here. And I will put chi of t. So I choose an approximation of my inverse, and I cut it at finite time, but a large time. I can compute what is S now, it's completely explicit. Somehow I construct first an approximate inverse before I construct the space, because it will guide me on what I should take for the space, for this A operator. So now S is just make a little computation. You apply x on this, you see that you get x applied to this is like dt. Then you integrate by part. You will pop up a lambda, which is good because we want minus x minus lambda. But then you also get a derivative of this term. So S is just given by I want to get it right. So it's the integral from t minus 1 to t plus or minus. Okay, I think it's minus exponential minus tx exponential minus t lambda, and it is chi prime of t. And now chi prime is a function like this. Okay, so this is really supported now between t minus 1 and t. So now the idea is that this flow is localized in a quite large time. So I need to try to now let's try to compute. I want that the norm of this operator is small plus compact on my space up A L2. Remember, H is up of A of L2. And I want to construct my A. So let's just, at the moment, just take a general A. So I want to compute up A. I assume that up A inverse exists. So assume A is constructed, and I'll try to A is such that up A inverse exists, and it's equal to up A inverse plus a smoothing operator. When I mean smoothing is like a smooth integral kernel. then what I can see is that if I compute, so I need to commute up of, I want to apply up of a minus 1. So I want to see how S act on H, which is up A L2. So I have to compute this operator on L2. But this guy is nothing more than minus T minus 1 T up A inverse. So up A inverse now, I'll put the inverse inside. Exponential minus Tx up A exponential minus T lambda chi prime of T dt plus something smoothing. So smoothing is going to be always compact. Compact because it map, for instance, it map a very negative Sobolev space, H minus n, to a very positive Sobolev space, because it has a smooth integral kernel. And you know that Hn embed compactly in L2 if n is positive. So it's a compact embedding. That's more or less as Guillarmou. Okay, so now the main thing to understand is this this operator, basically the pullback by the flow conjugated by this up A. So we need to get an estimate on this, assuming that A is a symbol, and this will guide us on how to choose the A. So if you remember what I said about the Egorov lemma was precisely computing up A conjugated by a diffeomorphism, in particular the flow. So I want to study this now. So remember Egorov lemma. So I have up A exponential minus Tx. And now I want to put an exponential Tx on the right. So then I said yesterday that this was up of A composed with phi t plus plus a remainder term. Plus, okay, so if A belongs to Sm, plus psi m minus 1. So when I mean plus, it means plus an element inside. And what is phi t? Phi t was, I defined it yesterday as the symplectic lift of the flow. So it's d phi t minus 1 x transpose xi, like this. So it's the symplectic lift, the action of the flow on T star m. Okay. So this guy now, this guy here, let's call it 80. Okay. I want to call it 80. So now 80 is equal to op a minus 1. Then I get exponential minus tx op a exponential tx, exponential minus tx. And this guy, by this Egorov lemma, it's op of a composed with phi t plus something in psi m minus 1 of t star m, of m. Plus something there. Okay, now I know that, and I want to understand AT on L2. But this guy is just a bounded operator with norm exponential C0t. Okay, so I can isolate it. So this guy bounded on L2 with norm big O with norm exponential C0t. So I forget it at the moment because I want it map L2 to L2. Now I want to focus on this part here. Okay, I have this. Now I have a composition of two pseudo-differential operators, so I can use the composition lemma. By the composition rule of pseudo-differential operator, I put a dot to say that you can, when you compose, you can take a psi m with a psi m1 and compose with a psi m2. So this is something in psi minus m because this is the inverse of the symbol, and the symbol was a symbol of order m. And this guy, phi t, is acting linearly in the fibers here. So it will not change the order of the symbol. So this guy actually belongs to psi m also. So I have a psi minus m with a psi m. So this is going to be an operator for order 0. And this guy is going to be an operator for order minus 1. Oui? Yes?
What is little a minus 1?
Well, it's the inverse, 1 over a if you want. I assume that a is just a positive, it's invertible somehow. I didn't construct it yet, I will construct it. But
No, I know.
It's 1 divided by a. So, now let's compute op of a composed with op, sorry, a inverse composed with a phi t. But this, by the composition rule, this belongs to psi 0 of m. And this is, we also know what is the principal symbol by the composition rule. We know the principal symbol of the product if the product is the product of the principal symbol, which means that this is actually op of a composed with phi t divided by a plus an element in psi minus 1. That's the class of pseudo-differential operator of order minus 1, which I defined yesterday.
You mean some element in C?
Yes, plus some element here. So maybe I should write it like this. It depends, yes, it depends on t. But t, you know, the main thing is that this will be compact. And t here will be taken large, but fixed. So it will just enter, this is actually a bounded operator from L2 to H1. Because I said yesterday that, if you remember, I said that, let's say if B belongs to psi S, or psi M in general, in fact B map any H Sobolev space of order S to H S minus M. So if you are of order -1, you actually map L2 to H1. And this embed compactly in L2 because we are on a compact manifold. So this guy is going to be a compact operator on L2. So the main thing now is to understand this. So what we want, this is a symbol of order 0, because phi t again is linear in Xi. So we want to estimate the norm of this. And if you remember, I said to get the norm of an operator of order 0, you need to look at up to a compact operator, you need to look at the lim sup of its symbol. So we want the lim sup of this symbol to be less than 1, strictly less than 1, when Xi go to infinity. So the norm of up A phi t divided by A from L2 to L2. So this was from yesterday lecture. This is actually less than 1 plus epsilon, for epsilon arbitrarily small, lim sup as Xi go to infinity of A composed with phi t x Xi divided by A of x Xi. So when I say this, I'm cheating a bit. This is up to a compact remainder. If you remember, I said you need to decompose it into A0 plus A1, and A1 was smoothing. But basically, now the main thing is, this is what I was saying yesterday, that somehow this pseudo-differential calculus, the nice thing is that you transfer all the estimates have been proved in one theorem, and then you reduce to just like constructing a classical observable. Yes, smoothing. Smoothing is compact. Huh? It's even better than compact. Smoothing means just smooth integral kernel. So it maps a distribution to smooth function. That's the best you can get for compact manifold. In fact, yeah, you're right, it's even smoothing here. So now we are in business if we are able to show that we can construct A such that A composed with the flow divided by A is less than 1. At least for here we are, the remainder was for t, the small t here was between big T minus 1 and big T, so for quite long time, for a dynamic where you have evolved quite far. And now you're even better than me probably to construct this guy, because it's just a question of dynamic. How to construct a function such that when I compose with the flow for a long time, is becoming much smaller than A. So how to construct it? What should I do? So this is where where there is something a little bit tricky technically, is that it's not possible to construct a function A which is a symbol of order m with m an integer. So one has to work in a slightly more exotic pseudo-differential calculus. We need to take a symbol which is of a variable order. So for this, one needs to take A in as, I will write it like this, m x c of T star m. where m is actually a symbol of order 0 on T star m. So we can define more generally, so when we have a symbol of order 0, we can actually define S of a symbol of order 0. And this is defined the same way. You just ask that dx, dxc alpha of A of xc is less with a uniform constant C alpha beta than the Japanese bracket, which was 1 plus xc squared 1/2 to the power mxc minus. So here, okay, there is something. I will cheat a little bit here. It's not completely correct, so for those who know this, forgive me. But roughly speaking, this is like this. In fact, one should put a 1 minus epsilon here, and then when we differentiate in x, there should be an epsilon loss also, but so I put this into quote mark in this one, but it's almost correct somehow. So this is the way you can define an order, a symbol of variable order. You define it the same way as I did with m real, except that m depends also on x and c.
The order depends on the direction.
Yes. 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 Exactly. Sorry? Yes, it's still true. And this will be again -1 here. And okay, of course you need to prove that when you take quantization of these guys, there is still the composition lemma, the boundedness, and so on. So the main thing is that one can extend everything I said on fixed order to this class Psi mxc of m. So this you have to trust me, but it's not very hard. It's just a bit technical. But sorry. What do you mean here? You just need this this type of estimate. Well, you need m to be a symbol. That's very. I mean, when I say symbol, it's a symbol of order 0. Smooth function and homogeneous of order 0 near infinity. Yeah, sorry.
Your functions are not defined in the 0 section, yes.
No, it's defined as smooth on near x equals 0. It's homogeneous for xi large.
Okay.
Everything which happened for xi bounded. Zero homogeneous, yes. Yes, it's bounded.
So, but then when you want to vary,
yes.
if A vanished on the 0 section.
No. A will be.
It doesn't vanish.
Yeah, it does not vanish. Yes. I will give you what is A. Okay, so we need to get this. So now I want to. Now, what we do, we choose A of xc to be xc to the power m xc, where m will be constructed. No, it does not vanish because this is not. This is 1 plus xc squared here. This xc. To be constructed now. So let's look. We want to construct it, and this will be guided by this a over phi t over a. So we need a of phi t of xc divided by a of xc to be smaller than 1/2, and this is exponential m composed with phi t time log of xi divided by exponential mx xi log of xi. So we need for t or for the large t that m composed with phi t time log of xi, sorry, log of xi composed with phi t. I'll write it like this, minus mx xi log of xi. We want this to be quite negative. So well, actually what I want is something like maybe some nu time t, sorry, minus nu time t for some nu. Well, so this is really now a question of dynamic. You have to look at how the symplectic lift behave. So what I need to do is the following. What I need to do, I need to take so this is the picture of T star. Let's say this is EU star, which was the annihilator of EU plus the direction of the flow. This is ES star. I want to construct, as I mentioned yesterday, I will take some cone CU near the unstable direction. I will take some cone near the stable direction. And the nice thing with this approach is that you can actually tune, you can choose CU and CS more or less as you want. I mean, you can take them very small or very large, and you can change a lot of, you can change quite a lot your what you want to do. And here, in CU, I will choose M to be 1. Maybe N, big N, let's say. Where N is let's say N is a positive number. More than 1. You fix an N. It's a weight somehow. And here, I want to take it to be minus n in this cone. And I also want to have the following property. I want that if I compose with the flow, m phi minus t. Oh, sorry, I think I... Yeah, I think I messed up. This should be phi minus t everywhere. So everything here is phi minus t because I just used the flow backward. Sorry about this. So it should be everything should be minus t here. Minus t, and so on. T is positive here, so that's fine. I want something negative. Because I will take this is exponential of this, so I want this to be small. So what I want is that this guy is actually decreasing for any t. That's one thing. And I want m to be equal to this minus n here and plus n here. So the flow is doing like this. in the fibers. So I want my M to be increasing. I want M to be increasing with the forward flow and decreasing with the backward flow. So then it's an exercise of dynamical system to check that this is possible. And I want this for any x and xi in T star M, let's say with xi large. What is important is just xi large. So I want M to be globally non-decreasing with respect to the forward flow, and to be equal to minus n here and plus n here. And
What is T large or positive?
Here I want it to be for any t positive or 0. Why is this? Is because I also, well, okay, in the end, I want this to be true for t large, this part. But if you come back to, here I just wrote s, but I needed also this q operator, which was the integral from 0 to big T, to be bounded on H. And to be bounded, you, this is, well, you need, no, but even, sorry, it's just, okay, but to be bounded, it's fine. It's just that to get this, no, yeah, I want to be bounded. So yeah, it's important to get it for all t actually because of the q.
So the difficulty is to have it for T large, it's very easy again.
I think both are not very hard. Huh? So, well, you have to construct it. You use the hyperbolicity of the flow. That's not very hard. In the neutral direction, you just take it to. You have to decompose into cone. In the neutral direction, you choose M to be whatever you want. Actually, you can take it to be large or small. It's quite flexible. The main thing really happens here in EU star and ES star, and I also want to in the intermediate cone, I want the M to be strictly increasing. So I want x tilde of M really to be bigger than some epsilon 0 positive, where x tilde is the flow, is the vector field of phi t. So in the intermediate region, I want it to be strictly increasing a little bit. So now, to check this, you have to look, for instance, in CS, in CU, so in CS, what you get is, you know that phi minus t x xi over xi time xi, sorry, minus 1 over xi minus 1 minus n, sorry. So M is, so I know that M is minus n in CS from here. I have to estimate. I just use the estimate on the linearized flow, and I see that this is less than exponential minus nu s time n time t for some nu s which is related to the Lyapunov exponent, the contraction rate in the stable direction. And if I look now in CU, what I get is a similar thing. Maybe there is a constant here, C, exponential minus nu u and t. So this is for t positive here. So you see that this is in both cones is actually decreasing exponentially fast. And n can be taken actually large. And now you have to look in the intermediate region. So this means this condition is going to be satisfied here because of these two cones. And the intermediate region, you need to look at this function, see how it is. Well, for instance, you can differentiate this, use the fact that this guy is positive in these cones, and you actually get this type of estimate. So I don't do the detail, but this is a little exercise. But if you choose it well like this, everything works, and you really get this. Where in fact here you can really take even nu times some big number if you choose well your function m. So that's the main thing. And well, you have to also prove that op of this is invertible. It's a bit of work, but it's not very hard. So that's more or less the main idea of this microlocal construction. So this is well detailed in Forge-Strand paper. So here I'm cheating a bit here because this is only true close in a cone close to EU star plus ES star actually. Because this comes from this estimate, and the increasing of m in this cone here. But everything what happened in the direction of the flow, we cannot gain anything because it's a neutral direction. So we will not gain in the flow direction from here. So it's only true in a cone close to the where the dynamic happens somehow. So now you need to take care of the direction of the flow. And in the direction of the flow, the idea is that the flow is elliptic in this direction. So it's differentiating in this direction. So its inverse is regularizing by one order. And this is encoded in this part here. So where is S? So now if you want, I have to look at this operator. So what I have proved more or less is that if I multiply my S, so what I have proved so far, we have shown that if P equal op of little p in psi0 of m is such that P of x and xi equal 1 in a conic neighborhood of EU star plus ES star, where the dynamic happen, then S times P is actually quasi-compact. So it's actually of the form, let's say, S1P plus S0P, where this is smoothing or compact, and where this has norm on H, which is less, H to H, which is less than some exponential, some constant, time exponential minus, let's say, nu time n time t time big T. Okay, because this came from the estimate I wrote here, using this. So I get a small norm if T, because T is large, so this is certainly less than 1/2, if T large. So this is quasi-compact. This will give me what I want. Of course, there is the lambda also to take care of. So if the real part of lambda is becoming negative, I have to take n a bit bigger to get it always less than 1/2. And now I'm left with S times 1 minus P, because I want to prove that S is quasi-compact. So now I'm left with S times identity minus P. Sorry? Yes, H is the op of A. H was op of A. Yes, A was this C to power M. So I'm looking at the norm of S on H, so I have conjugated by op of A to look at it on L2. Now I'm left with this, and now the idea is that this operator is actually regularizing in the flow direction, because you're averaging the flow. So it's like a function of the flow, a smooth function of the flow. So this guy, if you multiply by any power of x times S1 minus P, this is going to be integral from t minus 1 t. Every time you differentiate, you get a dt. So the dt move to this part. So maybe I put a minus plus lambda here. So every time you apply x, you differentiate in t. So this is bounded on L2 time p. It's bounded from L2 to L2. Bounded. And that's easy because it's just pulled back by the flow for finite time, and this is a zero order differential operator, so it's bounded. So it means I know that the principal symbol of x plus lambda of x and xi is equal to I xi x. So this is principal symbol. So it means that, and this is strictly positive. This is strictly more than I don't know, some C0 modulus of xi in a cone close to in the cone where p so it's 1 and 0 outside. So in the support of p for xi large. So p so you have the direction of the flow if you want. So this is E0 star. And the support of p is in the flow direction. The support of 1 minus p, sorry. So I know that the flow is actually elliptic in the region where I have localized here. And it's of order 1 here. So this means, using again a property of the differential calculus, that it means that this operator is actually going to be compact, because if I differentiate it, So I apply with a pseudo-differential operator for the one which is elliptic in this, where 1 minus p is micro-supported. Then I always get a bounded operator from L2 to L2. So this actually implies with the property of the pseudo-differential operator that S1 minus p is compact. Okay, so the idea, again, is that because I have localized in phase space near the flow direction, and in the flow direction I have an operator which is elliptic, so its symbol is really non-zero, it's more than xi. It means that this guy is regularizing actually in this direction. So it's actually compact. So it means this part will just be a compact error, and then then we're done. So that's the idea of this proof. So this show in particular, if you now lambda is the lower order term. So if I choose n, this is still true. So here. Okay, so I will not explain application to Mark length spectrum. Unfortunately, I don't have time. I've been too slow. So it means that for real of lambda bigger than minus n 0, there exists n such that if I construct M with this choice of n, remember in M there was this n which was the amount of derivative you put here and the amount of minus the amount of derivative you put here. It's like the Sobolev order. Then this operator S is going to be quasi-compact. So S depends on lambda a priori and equal S0 lambda plus 1 lambda, where this is compact. It's compact, it's analytic in lambda, holomorphic in lambda, I mean, and this has norm on H. So H depends on M here to H is less than 1/2. So this implies that minus X minus lambda is actually Fredholm and has finite dimensional kernel. So now I just want to tell you something about the kernel, because this is related to SRB measure or Gibbs measure in 1 or 2 minutes. So if you look at the kernel, let's take lambda equals 0, for instance. Now, what about the kernel? Lambda equals 0. So the kernel, you can, well, first, if you apply 1, it's 0. If the flow is transitive, then this is the only eigenfunction. So it's actually a smooth eigenfunction. So nothing very interesting here. But now you can look at the adjoint. What about the adjoint on H star? Then that's becoming more interesting because the adjoint acts on measure somehow. What you get is that in this case, you get one element in the kernel, the index is 0. I've been asked this question yesterday. We know that there exists one eigenfunction, so there must be one also for the adjoint. What you get is that you get an element, let's call it omega. And you can show that omega is a measure. So it's an invariant measure, actually. And this is actually belonging to this dual of the anisotropic space. So it means that if I apply op of xi, so the dual is actually given by applying xi to the power minus m to omega. This is belonging to L2. And the nice thing is that this m, you can, as I said before, there's a lot of flexibility in the m. You can choose it very large. The n here can be as large as you want. You can adjust the cone, take them as close as you want from the unstable direction, and so on. So you can really, using this, you can also show that these elements, they don't depend on the choice of m. This needs a little bit of work, but not very hard. So they don't. Once you have defined one of these m, if you change it so that everything what I said holds, you always get the same eigenfunction actually. So somehow the space is a sort of it's a tool, but the elements in the kernel, they don't really depend on the space. They are kind of intrinsic. And if you use this, you can show that actually the wavefront set of omega is included in EU star, ES star. So we know where are the singularities because of the way I define the wavefront set, and here because we're working with the differential operator. And in fact, in this case, W is the SRB measure. So somehow you can recover the SRB measure, and now if you add the potential, you will get the Gibbs measure. So that's what you will see. And maybe I'll stop here.
Thank you very much. Questions?
Yes. Yes. How I see it's SRB? Well, there are several ways to view it. Depends how you define SRB measure also, in the classical way. One way you can define it is by you start with a smooth measure, Lebesgue measure, and then you propagate it by the flow for a very long time, and you show that there is a limit. This is one way we can recover this. For instance, because the main thing is that how this guy is coming, it comes from looking at the inverse of x minus lambda, this resolvent. So if you look at the residue at lambda equals 0 of minus x minus lambda, so what this theorem what it says here, because lambda can be made to move, it means you really can invert this guy as a meromorphic family. So this guy is actually a meromorphic family of it's a meromorphic family in lambda of operator from H to H. Now if you take the residue, you will get 1 times this. So it's a rank 1 operator where it's just 1 on the left and this measure on the right. And this this residue, when lambda is positive, if you remember, I said that the inverse is given by this for lambda positive. Sorry, this is minus x minus lambda. inverse. So we have an explicit formula which converges for real part of lambda positive. So then you can really play with letting lambda go to 0 because the residue, it's like a scale limit of this, and you recover the classical. I mean, you can see that this guy must be the SRB measure in this case. And if you add the potential, you get the Gibbs actually by the same type of argument. That's somehow.
So perhaps we continue for the coffee break, and let's thank